Welcome back, everyone. Our next speaker, Han Chen, who's going to tell us about bracelets and theta functions.
All right, so thanks very much for the introduction, and thanks a lot for inviting me to give a talk in this wonderful conference. And yeah, I think, I mean, this workshop for class algebra is kind of very interdisciplinary, and we have class algebra but related to many different things. And here, what we have been related here are, so the bracelet here, change the color. So these are basically some topological object. And the theta functions, we have seen several talks in this workshop, and something this comes from mirror symmetry, but I'm not going to talk about theta functions because it will take too much time for 30 minutes. And finally, we have class algebra. I don't know where it is. Class algebra. For me, I mean, I start by learning class algebra from a representation theory point of view. So anyway, so these are something quite related to each other. So the overview. So I will first give you the overview of what I'm going to talk about in this talk. So we start with a surface with finite many marked points, and we will define the Skein algebra. And Skein algebra is defined topologically using the curves on the surface, or rather the union of curves. They are isotopic class. And then there are some special curves called bracelets, and they give rise to a basis. And conjectured, they are atomic, which I mean that it is the minimal possible positive basis. And conjecturally, they have quantization. And this was due to a series of works by Foucault from a more Teichmüller theory point of view, by Muschke, Schiffler, Williams from a topological point of view, and also Thurston. And now for class algebra, so if we choose any triangulation of this surface, and we can get a seed, and thus we can get an upper class algebra by using this seed T delta as the initial one. And then this upper class algebra, naturally, it contains the localization of this Skein algebra as the floating variables, namely the boundary arcs are floating class variables, and you localize it, it is still contained in the upper class algebra. And these two algebra, they are often the same for unpunctured surface. This was due to Greg Muller. And now for upper class algebra, you can use the construction from Gross, Heckenkiel, and Koswich, and also Davidson and Mandel to get something called quantum theta functions. And usually, usually they form a basis for surface type. So the result that I'm going to explain is that, roughly speaking, I mean, this is very roughly because strictly speaking, there are some corner case that you have to discuss. And roughly speaking, the quantum bracelets, which we are going to construct, they're equal to the quantum theta functions. And our construction work in full generality. So we work at the quantum level, and we can treat the punctured surface. I mean, most works concerning class algebra from surfaces, usually we only deal with the unpunctured case, because punctures will bring lots of difficulties. And we also will verify the conjecture that the bracelet basis is atomic. Okay. This is very roughly speaking. I will make it more precise later. And now I will give you a very quick review of Skein algebras. I mean, the detailed construction is not so important for our talk, but anyway, it will be pleasant to see a definition. So we work with the base ring, and we take the base ring as an integer. And if we are working with a quantum case, we take k to be the z2 plus minus square root. And our marked surface consists of a topological surface S that is of real dimension 2. Real dimension is 2. And it also consists of finite many marked points. And we require that each boundary component contains at least one marked point. And also those marked points inside the interior, these are called punctures. If in case that you don't know, I mean, I guess most of people in this conference will know that. And we will consider curves, by which mean the curve in the usual sense that either it ends at the ending points, marked points, or either it's a closed loop. So it takes a look like it is something like this, an open string, or it's like a closed string. So these are our curves. And the diagram is simply a union of many curves. And we use the bracket D to denote its isotopy class. And I will say that we will always consider the diagrams up to isotopy, by which I mean that we fix the max point and we fix the crossing, that isotopy are not allowed to change the max point and crossings. And we will denote D as a union of Wj, Cj, where Wj is the weight, or say the multiplicity of this curve Cj inside this diagram. And it will be called internal. I mean, it is not important, but it will make the definition easier if the diagram does not contain a boundary arc. And our Skein algebra is simply the 3K module, modulo the Skein relation. That the most important one is this one in my view. So this is a resolution of crossing. Whenever you have a crossing locally, you resolve it into two curves. And you also have some condition concerning the contractible arcs, that if something is non-homotopy, if something contract to a max point, you have some definition here. And now we'll make this Skein algebra into a commutative algebra by saying that two diagram, the multiplication is given by the union. The quantum version is quite easy. I mean, this is, if you have two diagrams, D and D prime, the multiplication is simply you put one above the other, and this will give you a non-commutative product. I mean, I will skip the detailed definition of quantization. I mean, you can imagine that you have to quantize the 2 and -2 here. And well, there are some natural definition. Okay, let me now talk about the class algebras. So assume that the surface satisfies some very mild conditions, and basically I want that the surface admit triangulation. And by an arc, I mean something which is not contractible and which has no crossings. So this is a curve ending at the max point. So an arc takes this form. So either it is like this, or it might be like this, but there are some hole here so that you cannot contract it. And we say two arcs or even two curves are compatible if they have no crossing. And we also have the notion called punctured case. I mean, if the surface has punctures, I think Fermi, Shapiro, and Thurston, they introduced the tagged arc. So tagged arc is something, if you have a puncture here inside the surface, you have to say that sometimes you want to add a small tag here to say that this is something different. That is not important for us. You just know that there are some more arcs. And we can also talk about the compatibility, which means that there's no crossing, and one have to define what do we mean by compatible tagging at the puncture. Now, a tagged triangulation, or simply a triangulation, is a maximal collection of non-isotopy arcs, which has no crossing between each other. Starting from a triangulation, we can construct a seed. So the class variables are simply the arcs inside the triangulation. Quiver is the oriented graph, and Müller has introduced the quantization of this seed for unpunctured case. And let me give you a quick example. So you look at this annulus. This annulus, I have already drawn its triangulation. So this area bounded by B1 and B2 can be divided into two triangles. And there are internal arcs, X1 and X1 and X2, and boundary arcs. And if I draw the oriented dual graph, it will be something like this. So in the end, we arrive at something like this. So we have X2. There are two triangles contribute to two arrows from X2 to X1. And we have this B1 and B2. And arrows is from X1 to B1, okay, this direction. This direction. And you see immediately that if you only look at the unfrozen part, unfrozen, or say the internal part, internal arcs for this quiver, that is X2 to X1. This is a Cronite quiver, and its rotation theory is well known. And also this annulus, it has infinite many triangulations by rotation around the boundary. Okay. From Skein algebra to class algebras, so you already have a triangulation. So our logic is like you start from a surface, you can construct the Skein algebra. But you can also choose a triangulation. Now you get a seed. Now you take this as an initial seed, you can construct a so-called what I call partially compactified class algebra A bar T delta and upper class algebra U bar T delta. And by partially compactified, I mean that frozen variables, or say boundary arcs, so these are just boundary arcs, they are not invertible. They are not inverted in this algebra. And you can also invert them like we usually do for class algebra. So this gives you the usual notion of class algebra A and upper class algebra U. And the Muller has shown that for unpunctured surface, the Skein algebra is contained between the class algebra and upper class algebra. And there are under mild condition, they are the same. Under mild condition, that means that you have enough marked points. They are the same. Okay. So let me end this introduction to Skein algebra and class algebra with a dictionary. So on the topological part, actually you are looking at Teichmüller theory or the SL2 local system on this marked surface, and you compare it with the class theory. So the triangulation goes to is in bijection with C. Text arcs are class variables. Boundary ones are frozen ones, or what we usually call coefficients. And the union of arcs from the same triangulation, these are class monomials. And taking the union is the multiplication, and flip is, well, I didn't explain that. So flip is what you change the triangulation. So you change the triangulation like this. This is the flip, and this is the mutation. So I assume that you already know something about class theory. So let me explain the bracelets. Well, so here in this example, we have a loop L. So this is a very easy non-trivial loop. And the bracelet WL, this is what I call the bracelet loop. This is a loop with W minus 1 self-crossings. So here you see that if you go around this annulus twice and using a closed loop, this will give you the bracelet 2L. And if you go around it 3 times, this will give you the bracelet 3L. Well, these are curves which has self-crossing, but it turns out to be the correct things to look at. And the bracelet diagram, brace D, by which I mean it is a compatible collection of arcs and bracelets. So the arcs and bracelets, they must not intersect. If you look at this diagram and you consider all the internal bracelet diagram, which I mean that I don't allow the boundary arcs inside, this gives you a basis over the coefficient ring over the boundary, such that if you want something which has no self-crossing, either you take the class monomial, by which I mean that I take the multiple of x1, x2, so you take something like this, so this x1 square, x2 square, or you take some bracelet diagram. So you only have two choices. In general, the bracelet diagram can be more complicated. Okay, so these are lots of curves, and what we say that the Skein algebra elements represented by this diagram, they form a basis, the so-called bracelet basis. And how do you compute that? So we have notion called Chebyshev polynomial of the first kind. So these are denoted by TW, a single variable polynomial. So such that TW acts on Z plus Z minus 1 give you the ZW plus Z minus W. Well, you can write down the recursion. So the T1Z is Z, and you have a recursive definition. And the important part is that the trace of a matrix, a monodromy matrix. This is a monodromy matrix for this SL2 local system. It is represented by some matrix in SL2, and if you take the trace of going around W times, this gives you the Chebyshev polynomial of going around the single loop. So this is why Chebyshev polynomial is related to this SL2 situation. And it was proved that the bracelet diagram, so the bracelet loop, they are computed by this Chebyshev polynomial from a single loop. So as an example, in our previous example, so you have this bracelet 2. So this is bracelet 2L. And you use the Skein relation, this gives you something like this. So this is L squared and minus 2. So these are exactly the Chebyshev recursion. Okay, so far I have given you the definition of bracelets, and now we have notion called the atomic basis. An element in the upper class algebra is called universally positive if you take any seed and you write it as a Laurent polynomial in that seed, then its Laurent coefficient should be positive, by which I mean that if you work at the classical level, it should be integer, natural numbers, and the quantum level, it should be NQ plus minus. And a basis of the upper class algebra is said to be atomic if it consists of universal positive elements, and moreover, it is minimal possible. So this is what we mean by atomic. So it is minimal possible, which I mean that any universal positive elements is in fact a positive sum of the basis elements. So by definition, the atomic basis is unique, but if it exists, but the existence is open in general, I think. And the conjecture by Goncharov in a slightly different language, and also by Mushka-Shiflin-Williams, is that the bracelet form the atomic basis. Well, I think the people need some choice of coefficients. I have not gone through all the literature, but I think for example, in the second case, maybe we need principal coefficients. But anyway, we need some choice of coefficient, and we want that bracelet form an atomic basis for the upper class algebra. And we don't know how to prove that for the moment, but we know something similar. So in the later development of class algebra by using the scattering diagram, Gross-Hacking, Q, and Konswich, they introduced the theta functions. And they showed, and in this case, if the no conductive component of the surface is a west punctured closed surface, by which I mean that is some surface like this. So it's a surface without boundary and with a unique bound point. If it has no component like this, then the theta functions form a basis. This was due to Gross-Hacking, Q, and Konswich, and by result of Yuri-Gusan, I think. And then Travis Mandel further showed that this theta basis is atomic. So our situation is that we want to show the bracelet from the atomic basis. But what we know is that theta functions are atomic. So it is natural that if you can show that these two are the same, then you get the conjecture. Any questions so far? Okay, so let me go to the conjunctions and results. So two seeds are said to be similar if they share the same Froden variable, same unfrozen part. So for example, if you have a seed like what we have seen previously, if you have seed like this with two frozen parts, so this is x2, xy, right, with boundary, and you might think of the principal coefficient, and you might think of the coefficient-free case, and all these guys, they are similar. And why do we care? So this kind of similarity of seed was considered in my previous work for considering basis for class algebras. So the important part is that the importance of similarity is that similar seeds share similar structures and properties such as basis. So if you take the class algebra running from this kind of different initial seed, it turns out that if you know the basis for one seed, for one class algebra, you know the basis for the other class algebra. Now about the quantization. For the unpunctured case, the quantization of the Skein algebra and the initial seed, and as well as the upper class algebra was due to Muller. But for the punctured case, there's a big problem, obstruction in that the Skein algebra, well, I'm not so sure about Skein algebra maybe. Let me just talk about the class algebra. So the class algebra cannot be quantized if you only take the natural seed from the surface. The reason is that the change matrix, or say the adjacency matrix for this quiver, is not a full rank. So by definition, you cannot find a compatible pair which quantize this class algebra. So our strategy is that we can choose a different seed which is similar to the original one. So a situation like, for example, if you have a seed, if this is your seed, it is not a full rank, then you can take, for example, principal coefficient or whatever coefficient you like, so that you can do the quantization. So this part can be quantized. So this is about how do we quantize the class algebra for punctured surface. And what about the tagged? So a tagged bracelet diagram, this is a union of compatible tagged arcs and compatible loops. So by compatible, I mean that they have compatible tagging and they have no crossing. Now I want to define the class algebra element for this one, because recall that we do not have Skein algebra. We do not have this one now because we cannot contact it, but rather we have the upper class algebra. We have upper class algebra, and this can be quantized. So now we have to define this algebra element in this quantum upper class algebra. So if you are given a tagged arc, you simply take it to be the quantum class variable corresponding to this tagged arc. I mean, the set theoretic bijection was well known due to forming FST. This was well known. Now the set theoretic bijection, so you simply take it to be the corresponding algebra element. But there was one exception. I mean, by treating with surface, there was a lot of exceptions. One exception that this bijection does not work for once punctured closed surface, because for once punctured closed surface, there are more tagged arcs than class variables. So how can we define the algebra elements? We defined it using the projection from a covering space. So it is like, assume that you are given a once punctured closed surface, and you have a tagged arc, maybe like this. You have a tagged arc, right? And you do not know how to compute this one. Now you take the covering space. So the covering space is like this. So you cut out from a point, and you cut it out. You put 2 copies of your surface, or you can put D copies of your surface. You cut it out. I mean, I want to cut it out from a loop on the puncture, but you can cut it out anywhere. And now you have 2 punctures, and you glue them. You can glue them. Now this one, you have a bijection between tagged arc and cluster variables. And now you can define the algebra element. Now finally, you take the projection, you can define it this way. I mean, this projection from a covering space. For the moment, we do not have a more natural definition. I mean, the unpleasant part is that you have to distinguish the closed surface and non-closed surface is something not very convenient, not very pleasant, but it works. And for the loops, you can define it using a quantum trace of these bracelet loops, following the work of Bonhong Wang and also Allegri and Kim. I mean, if you take the quantum trace, you do the calculation in the class boson algebra. And this, by which I mean that this algebra generated by the X variables. And the old algebra, which I mean that they generated by A variables. If you are working with the class boson algebras, the change of coefficient does not matter. So you can calculate it over there. And finally, for this diagram, you simply define the algebra element as a product from each factor and modulo a correction term by the Q. Because you want bar invariance, you have to put a Q alpha over there. So then, well, the most non-trivial part is that how do you treat the loop and use the quantum trace, and how do you treat the closed surface? You use the projection. Okay. Now we have defined a tagged bracelet diagram. The theorem is simply that assume that there's no component which is a once punctured torus. So we include this part. Once punctured torus, we don't like it. Then we claim that the corresponding algebra element is simply the quantum theta function. So why once punctured torus is not good? Because they simply are not the same. So the work by Zhou Yan, she calculates them explicitly for punctured torus. Once punctured torus, the tagged arc, they are not the same as the theta function for the once puncture in this case. And by this theorem, more or less, I'm sure about this. I mean, we haven't written down this yet, but we think more or less this is clear to us now. So if you are working with the class scattering diagram from GHKK, and you compare it with the stability scattering diagram from Bridgeland, they only differ by non-trivial incoming wall for the once punctured torus, so corresponding to this case. And they are the coincide for all the other surfaces. So this was kind of implication by this theorem. because in these two kind of diagram, for the first diagram, you are calculating the theta functions. For the second diagram, you are more closer to calculating the text arcs or some Teichmüller theory or representation theory. Okay. And there's a corollary. So assume that no component is a once-punctured closed surface. In this case, we know that theta functions form a basis. Now we know that the text bracelet, they are the theta functions, so they form the atomic basis. This was simply a corollary from this theorem and our previous property of theta basis. Okay. So maybe in the last 5 minutes, I will tell you the strategy about how this can be verified. So we want to verify that the algebra element you defined using the union of diagrams is a theta function. So the first one is a surface in general is too complicated. So I want to say that we can cut the surface and work locally in the subsurface. And because the Skein relation calculation is local, well, we also need some actual work to show that this works for theta functions. I mean, there are some works to do here. But for surface type, we can do this. And now the difficult part is that, I mean, because the tag arcs are something we more or less know very well. So tag arcs, these are class variables, and they are theta functions. So these are something we know very well. But the loops are something more complicated. We need to verify that a bracelet loop of winding number W is a theta function. To do this, we use a Dön twist in the argument, and we have to verify the Chebyshev recursion, because the theta function satisfies the Chebyshev. The bracelet satisfies the Chebyshev recursion, and we have to verify it for the loops. And the Dön twist around L, around a simple loop L, in case that you have forgotten, is that if you have a gamma which pass through a Dön twist, pass through a single loop, then the twist is that you go towards this oriented loop, then you do a travel around it and you go forward. This is our Dön twist. And assume that you can verify step 2, which requires lots of work. Then you can verify the step 3, that if you take a union of loops and arcs which do not intersect, now you are confident that this should be a theta function. And the argument is not trivial, but you have to follow the same spirit as step 2, and you try to make the Chebyshev recursion verification something, well, adapted the argument, but the arguments are similar. I want to say that the ideas are, in my view, are kind of natural, but the rigorous arguments are very subtle because you have to treat different kinds of surfaces and very lengthy. So for the moment, our paper to appear has more than 100 pages to do all these arguments. Okay. And finally, I want to say, how do you verify for a single loop? Assume that you want to verify a single loop is a theta function. So you can, as I said, you can work it locally. So you cut out the subsurface which contains a single loop and you verify it. So now the single loop, either it is contained in an annulus with 2 mark points, this is called annular type, and you can do the calculation explicitly. Or you can put it in the subsurface of this type. So it is a high-genus subsurface with exactly 1 boundary component and 1 mark point on it. I mean, the representation theory is a bit complicated. The module has dimension 2, 2, 2, 2 on every vertex. And I tried to do explicit calculation. It was too complicated. So we use some argument trick to show that this is a theta function. So a single loop is something you are confident that you can do because you reduce to 2 very simple surface. And now you want to do it for this bracelet loop. So this is something more complicated. And so in general, a theta function, theta g, can be computed as a Laurent polynomial by choosing a reference seed, t delta prime. So in fact, we choose a generic base point in the chamber corresponding to this seed, and we calculate the Laurent polynomial corresponding to it. So this was a calculation carried out in sketching diagram. And now this Laurent polynomial, it can even be computed order by order. So in the sketching diagram, it is that you calculate it in a finite order sketching diagram. So by order, I mean that you view the initial class boson variables in the initial seed as infinitesimal. So the higher order of initial boson variables, the higher the smaller you view it. Now it's a fact to show the Chebyshev recursion also works for the for these theta functions, because we know that the bracelet, this one has Chebyshev recursion. Like this. So it remains to check the Chebyshev recursion for the theta functions. Now, it's fair to check it for some reference seed. So you start with any initial seed, and you apply the D twist around the loop for many, many times to obtain a new seed. In the language of Uri-Gusai, actually, this means that you choose a base point close to the G vector of loop, close enough. Now then, for this very special space, very close space point, the theta functions can be written as a Laurent polynomial with a leading power. So this is a G vector, and this is a Laurent monomial with a negative of its leading degree, and with higher order terms, by which I mean the higher order in the sense of scattering diagram or in the sense of class boson varieties. And now by this formula, you see that immediately you see that this theta function, more or less, it is the Chebyshev polynomial of the degree 1 of the Whiting number 1 theta function, modulo some higher order terms, right? Now you take this n to infinity, you get the equality, because you know that both of them are Laurent polynomials. So yeah, this is how we do it for this proof, and I skip the rest part of the proof, and thank you for your attention.
No.
Okay. Oh, maybe I forgot to send the link of the slide in the chat. Maybe put it inside. Okay.
I still don't hear anyone talking from the room, but try it.
Can you hear me?
Yes.
Yes, I hear you now.
Oh, good.
Okay.
So sorry, we had some audio problems here. Well, first of all, I would like to say thank you for your nice result. I'm really happy about this. This is Ralph. Could you go back to your main theorem page?
Yes.
Yes. So in the theorem, you exclude the once punctured torus, but in the corollary, all once punctured closed surfaces. Is it still a basis? Do you just use atomic property, or is it also not a basis?
Yes, I mean, yes. This atomic basis, I think is a very unpleasant part. So it's like you know, usually we have the so-called we are talking about the so-called full fork and control of conjecture. So usually it is a question whether the theta functions form a basis for the upper class algebra or not. So if it is not a once punctured closed surface, the cluster complex is dense in the scattering diagram. So we know that it is a basis. And in general, we only know that it spans the middle class algebra. So it is, in general, it is a sub algebra inside. Mm-hmm. So yeah, so there are lots of difficulties for this part, because the main reason is that the class complex, they occupy a half plane, only a half plane. So all the theta function stuff about the atomicity, they are talking about the atomic with respect to all the atlas, all the basically all the reference point in the Euclidean space. But now, because the class complex only form a half plane, so we can say that the theta function, they are atomic with respect to the scattering atlas, but we do not know if they are atomic with respect to this class complex. So there are different versions of this universal positivity. So basically, usually in class, as a class, people want to talk about universal with respect to the class atlas. But usually for theta functions, you know that it is atomic with respect to the scattering atlas. And if the class complex is not dense, these two atlas, they are different. So there are two different notions. We do not have counterexamples saying that it is not atomic, but we do not know how to prove it using theta functions. Mm-hmm. So it is still open in some sense. And in general, although that we do not know whether the theta function form a basis for the upper class algebra, I think it was known that the bracelet without tag, the bracelet form a basis for the Skein algebra itself, right? Mm-hmm. So, right, I think it was proved by Thurston. So you take the bracelet, you take no tag, and I think that this one is a basis for the Skein algebra. And here there are also lots of difficulties. So there's a difficulty about this difference between cluster atlas and scattering atlas. And also so it is not of full rank. So the class theory here, so the seed here is not full rank. So this is a very bad situation to study basis for class algebra because the Y monomials, they might be linear dependent. And it can be very difficult to distinguish different F polynomials in some sense. So yeah, for one punctured closed surface, I'm not sure. We do not have counterexamples, but for the moment, I don't think our tools or our knowledge is enough to treat the one punctured closed surface atomically.
Okay, thank you.
Hi, thanks so much for the talk. I had a couple of questions as well. Yeah. So when you put some marked points on the boundary of the surface, do you mean Gmod B flag there or Gmod N flag?
I don't know. I mean, I use the class algebra definition. I'm not sure. So yeah, because maybe, I'm not so familiar with the full control construction. I think it should be Gmod.
But yeah. Do you put frozen variables on the boundary of the surface?
Yes. Yes.
You have,
I put frozen variable on the boundary. Yeah.
Thanks. And also one other question is, so when you talked about this projection from kind of double cover of the surface to the surface in the quantum case, is this this projection? Do you get an algebra homomorphism somehow?
Yeah. So it is a way. It is intuition to give you the definition. I mean. This is the intuition how you define it, but in reality you define the quantum class algebra for these two guys. So what you are going to project is not Teichmüller theory, but you work with the quantum class algebra for these two guys. Right, and in particular, you can show that the quantum class variables from can be projected in this way. I mean, we are not doing a. There's a. I don't quite remember. There's a algebra homomorphism for if you choose the coefficients very carefully, there's a homomorphism between quantum class algebras. You have to choose coefficient, for otherwise it cannot be quantized. So these are UQ for some. So you have some triangulation delta here, delta tilde here, and now you choose some CT here, which is similar to T delta but not the same. And now you choose some beta coefficient for T tilde, and now you do the calculation from this one. I think this was the idea. So there's a projection of seed and projection of scattering diagram in some sense.
So this projection, this is not a homomorphism of quantum cluster algebras.
I don't quite. I think it was algebra homomorphism. At least at the level of quantum torus, it was an algebra homomorphism, and that is what we need for calculation. At the class algebra level, I remember there are some subtle questions here, but I don't quite remember the details for the moment.
I see. Thank you.
Okay.
I think it's on. Okay, so let's thank Fan again. If you have other questions, you can ask him during the break. And we'll take a 5-minute break.